recording. Okay, welcome everybody to another weekly Bootstrap seminar. Today we're very glad to have Vladimir Kazakov. He'll tell us about the matrix Bootstrap revisited or something along those lines.
Yeah, you're almost right. So I'm sharing the screen. Is it visible?
Yes.
Good. So hello everybody. I'm very happy to talk here on this Simon's collaboration workshop, especially that I'm an outsider and I'm pleased that this possibility I have this possibility to talk in front of the specialists in the subject. I will speak, actually I changed a little bit the title. I called it now Relaxed Matrix Bootstrap, and I hope it will have a double meaning, this first word. The talk is based on the work with Zhechuan Zheng, who is present here in the audience, and he is the one who is really behind the numerical kitchen of this project. So if there are some subtle questions about the details, he might help me. Okay, now so the main subject of this talk is the computation of multi-matrix integrals of the kind I show here, like multiple integrals over Hermitian n by n matrices, and with the weight exponential of trace of any function of these matrices, invariant function of these matrices. It could be also applied to unitary matrices, normal matrices, but we will work with Hermitian ones so far. So there are many applications of such matrix integrals in mesoscopics, in two-dimensional quantum gravity models, in statistical mechanics on planar graphs, and even QCD. In Yaguchi-Kawai reduction, for example, it's a multi-matrix model, and so on and so on. But and will be interested in large N computation of those integrals, and at large N they are functional integrals, actually, having infinitely many degrees of freedom. They are rarely exactly calculable and very difficult for numerics also. And essentially, the only universal reasonable numerics was so far Monte Carlo. We'll compare our results with Monte Carlo at the end of the talk. But before, let me mention some solvable examples to warm up to the unsolvable problem. Say the one matrix integral, which we'll consider here as an example, is the most famous example of the matrix integral. It's known that in that Hopf limit, it sums up the planar graphs, like it's drawn here. And a slightly more sophisticated example is the two-matrix model, with matrices having arbitrary potentials and the simplest interaction, like AB in the action. This model also is solvable, and using it, once I define the so-called Ising model on dynamical graphs and computed all the critical indices of it, etc., etc. So there are useful applications of these multi-matrix models. And a slightly more sophisticated example of solvable matrix model, if you replace this trace AB interaction by trace of any function of AB, then it can be solvable in terms of character expansion methods. But there are not many examples of, there is a very narrow class of these solvable matrix models. And we will consider, of course, an unsolvable example, at least at the end of our talk, to show the power of the Bootstrap approach. Then we replace this AB interaction, we'll replace this AB interaction by trace of commutator square AB, which is already unsolvable. At least I don't know how to solve it. And matrix bootstrap is a new numerical method inspired to a great extent by conformal and arithmetic bootstraps. It was originated in the papers. I would say the pioneering papers were Anderson and Kruchensky. They applied it to young mills on the lattice, but the method is there. And also Lin's paper about 1 and 2 matrix models. After our paper, there have been a few other papers on this on various aspects of this subject, and I think this is a new subject, still having a lot of potential for new results. Our contribution will be to significantly improve the methods of Lin using the relaxation procedure. So this will be the second meaning of the word relaxation. Okay, so this is about the models. And now, what is the matrix bootstrap? First, we'll start from the example, which is not matrix example, just the computation of moments of this simple non-Gaussian distribution with the coupling G here for non-Gaussian term. So we define WKs as moments here. Just by invariance of the measure with respect to the shift of x, we immediately write down a sort of word identities for this integral, which for more complicated models we will call loop equations. So they relate even moments because due to x2 minus x symmetry, d2 symmetry, the odd moments are 0. So it's the first ingredient, sort of equations of motion, and the second ingredient is the obvious inequality. If we take sum of powers of x with arbitrary coefficients and integrate it with this distribution, it's certainly a positively defined quadratic form. So it's positive for any for any vector alpha defined by its components here, and it can be reformulated as the positive definiteness of the underlying quadratic form, which is formulated here in terms of these moments. Oh, sorry, and this appears as a new condition, which I mean, of course, if we have such a simple analytic problem, we can get along without it. But now we will, of course, truncate the system of these equations, and then this positivity condition will be very important. So this is the setup, analytic setup of Bootstrap, and numerical Bootstrap. In numerical Bootstrap, we will do as follows. Practically, instead of finite number of correlation instead of infinite correlation matrix W, it is infinite, of course, in the previous transparency. We'll take its finite minor of the size lambda plus 1, upper left minor. We call it W lambda, truncated correlation matrix. And using the loop equation, we can, of course, it contains only finite number of moments, and using the loop equations, we can express all these moments in terms of a single moment W2 and plug it into this correlation matrix because it consists of higher moments. Now, now that we can apply the reduce command in Mathematica. It's very simple to find the maximal and minimal value of W2 when we impose this inequality. I remind you that W lambda, each matrix element is already a function of W2 and linear actually, W2 in this simple example. And then a finite lambda, which we call cutoff, we will discover the inequality on W2 between minimal and maximal value for a given lambda. And for example, for just very generic value G equals 1 for this coupling, which we have in non-Gaussian coupling G, and lambda, the cutoff equals 10, which means that W, we take maximum W20 here, the moments up to W20. We get an inequality which appears to be very close, like 7 digits here, very close to the exact value which we can compute, of course, in this integral, because it's computable in terms of basic functions. Okay, and then for if we scan G, we find the following picture. The dotted line is exact solution, and then you have these colors which go from lambda equals 2 to lambda equals 3, 4, etc. And this maximum and minimum, for example, for lambda equals 4, you have this this is gray area which surrounds the exact solution, and already for lambda equals 10, it will be indistinguishable from the dotted line on this picture. Okay, and why does it work at all? We'll show that from the solution of Hamburger moments problem, the famous Hamburger moments problem, which I formulate later, we certainly expect that at lambda going to infinity, at cutoff going to infinity, the upper and lower limits, of course, will collapse to the correct value, and that can be really shown. So the correlation matrix plays an important role. The positivity of correlation matrix plays an important role in this system. Okay, this is about the simple example. If you have questions here, it's a good moment to ask. Otherwise, I go on with the next topic. I will explain what is the Hamburger moments problem and the solution, the theory behind it. And actually, for one matrix model, for this simple integral and for one matrix model, this provides us with the theorem. The Hamburger moments problem provides us with the theorem which shows that indeed approaching lambda equals to infinity, we approach the exact result. So the theorem goes as follows: that if you have an infinite series of infinite sequence, sorry, of integers, not integers, of real numbers nk, we can always find a positive Borel measure mu such that the xk integrated with this measure d mu of x gives you produces precisely mk. So you construct the measure using the moments. And this is possible if and only if the matrix M k plus j minus 2 is positive semi-definite. So this is the first part of the theorem, and then if these numbers grow not faster than factorial, then the measure is unique. And of course, we can immediately apply it to our integral, and moreover to the one matrix model as well, which we start studying on the next transparency. But before, I simply have some comments that the approximation and numerics are based on finite cutoff, so that we use the lowest moments and the finite correlation matrix. But the inequalities at each lambda, which we obtain at each lambda, are rigorous in the sense that in increasing the cutoff, we can only improve the inequalities. The theorem is not immediately applicable to more complicated problems, like the multi-matrix model. The structure of correlation matrix is more complicated in the multi-matrix model. Then we cannot apply directly this theorem. But nevertheless, the bootstrap approach to various large N matrix series gives very promising results, as I am going to demonstrate. Now I come to the one matrix integral, and I remind you that this is the integral, and it can be solved by simple observation that if you diagonalize a matrix M, like X is a set of n eigenvalues and omega is the rotation matrix, SUN rotation matrix, then by going to the measure in terms of X, you get the following effective action: the potential, which is just for each eigenvalue V of X, and then there is an interaction produced by the Jacobian of the measure, the Dyson measure, so-called Dyson measure. And at the large N limit, we simply compute the extremum of this action and study all the set of possible extrema. One should say that this model looks like this problem looks like a static problem for two-dimensional Coulomb charges living on the line a priori, on the X line, so that when they're in the minimum, of course they will be say in some well. Suppose this is the potential V of X, then the eigenvalues repulse each other. Then they will be distributed with certain distribution in this well or in that well, but we can also fill the maxima by some portion of this eigenvalue. For example, if you fill this maximum, of course, it's not a minimum, but the maximum, just the extremum, which is not stable. Then the cuts containing eigenvalues, the distribution, turns into along the imaginary axis. These two axes are real and imaginary axis of X in order to solve this. The charges, so that in the large N limit, the minima and maxima of effective potential create real and complex cuts respectively. And we will call physical solution such that it has only real cuts with positive density of distribution of eigenvalues, so that we don't feel the maximum of the potentials anymore. The solution is very easily given by the result, which is expressed through this potential derivative of potential. There is a square root here, which creates these cuts, and the polynomial P of X is completely fixed by the distribution of by the distributions of eigenvalue, the numbers of eigenvalues in each well, and also by the asymptotics at large X. And the density is the imaginary part, at least for this real cuts, it's imaginary part of G on the cut. Using this density, we can compute the moments, and of course, for physical solutions, excluding these complex cuts. For physical solutions, it's a positive measure, and all the moments represent real numbers, which suggest the application of Hamburger momentum problem here. Okay, then this is then we can also introduce the positivity of correlation matrix. Namely, we define the matrix operator O, which is the sum up to the sum of powers of the matrix with arbitrary coefficients up to some kappa of lambda. Then we construct the quadratic form, whatever, or trace. And this quadratic form is, of course, positive by definition. That means that the matrix, which looks precisely as it should be in the Hamburger problem, depends on K plus J only. So this matrix should be positive defined for physical, and we'll show that it's natural that it's positive defined only for physical solutions having real cuts. One can, using Hamburger problem solution, one can really formulate the following theorem. One can observe that the resolvent G of Z, which is the sum over momenta with powers of Z, is given, of course, in terms of this integral over the supports. And this is a function analytic for Z everywhere in the plane Z, except of the supports of the eigenvalues, except of these cuts. Then physical G of Z cannot have complex cuts because rho of X is positive defined. Yes, it's a real positive defined function for physical solutions. Conversely, it's easy to see that if G of Z does have complex cuts, then some momenta will be either not real or even non-positive or non-real, at least. And this suggests the following, applying the Hamburger problem, this suggests the following statement that positivity of correlation matrix is in one-to-one correspondence with reality and positivity of eigenvalue density. So that we, using the positivity of correlation matrix, we pick up only minima of effective potential and not the maximum, not the unstable points. Otherwise, we of course can have all this minima using the positivity of correlation matrix. Okay, and this justifies analytically, I already pronounced it, that my matrix Bootstrap picks up on the physical solutions of one matrix model.
Sorry, can I ask a naive question?
Sure.
So if we are the defining contour of the eigenvalues, if it's a Hermitian matrix integral, is real eigenvalues. But integrals, I mean, it can have a saddle point which is not on the real axis, right? So in this, what you said, G of Z cannot have complex cuts. Like this configuration you drew could contribute as maybe a subleading saddle point or something, no?
I'm not sure I understood. What?
I'm saying we convert the one matrix integral into some integral over the eigenvalue density.
Yes.
But it's permitted to have saddle points that are not on the real axis, right? So
In principle, yes, like this cut, for example.
Yeah. So why are you excluding these guys, or
No,
somehow
I'm not
are
excluding. This is the matrix bootstrap which excludes them. I mean, if I want to apply the bootstrap and, for example, numerics, then I only can pick up the solutions which are minima and the real distribution. That's the statement.
Okay, but you can have like a matrix integral in which these maximas contribute. They would just not be captured by the method.
Absolutely, yes. The positivity of correlation matrix excludes this kind of cuts. That's the statement.
Oh, okay, thank you.
Okay. Now, numerics for one matrix model. It combines the positivity of correlation matrix and the loop equations for all moments up to the order 2 lambda. Lambda is cut off. As an example, we take the quartic potential as the matrix potential, the same one as in single integral example, and the loop equations for moments appear to be of this form. They are already non-linear. I don't say how to derive them here, but for the specialists and matrix models, it's the standard stuff. It's like McKay-Comic-Dahl equation in PCB, but I will later show schematically in two matrix model. Okay, this is the equation, and then the correlation matrix, which we compute as this matrix of momenta, is positive semi-definite. It has only non-negative eigenvalues. I should have marked here W lambda because I mean already the finite minor, minor out of the infinite relation matrix of the size lambda plus 1, lambda plus 1. Then we solve loop equations. Again, we can solve all the higher momenta up to lambda order in terms of W2. And the same story, we plug it with non-linear expressions, plug them into the correlation matrix and solve the inequalities using, again, just Mathematica program. And we get the upper and lower limit of W2 moments, the lowest moment, trace m square, at such a cutoff. And here is the result already where we scan G, the coupling. So you see that it improves with each lambda it improves, and for lambda equals 6 or 8, you almost don't notice the difference from the exact analytic solution. But what is interesting here, of course, that you can go to negative couplings, which means that instead of this picture for Coulomb charges, you have rather that picture. So it's unstable at finite n. It's an unstable potential, but still there is a solution, the local maximum, where the eigenvalues are squeezed between two maxima, and at least up to some critical value of GC. You have a solution. This critical value is something like -112. So it goes here, and Bootstrap still captures very well this quite unstable region, although it's the approach with lambda, increasing lambda, is slightly slower here than for the positive G's. Okay, so this is about one matrix model. And now so again, I repeat that the Hamburger momentum problem, the solution for Hamburger momentum problem, provides us with the firm ground of application of this method in one matrix model, because the correlation matrix has this form. It depends on K plus J. But now we go to more complicated examples. Sorry, I want also to discuss the Bootstrap for symmetry breaking solution for one matrix model, because here we, for these two solutions, we don't break the x to minus x symmetry. We see all the distributions asymmetric for these potentials. But we can also take the symmetry breaking example by using the double well potential. We flip the sign in front of x squared. Then you have two phases. You have unbroken Z2 phase, where the eigenvalues are distributed over this barrier, and then still it's symmetric distribution. The numerics for it also converges quite quickly. So to the analytical answer, given by this black dot. So slowly this island, sorry, there is something unstable in my computer. Okay, this island slowly vanishes around this analytic solution. A good model for global warming, I think. Okay, then let's take the broken T2 phase when we are below the critical point, and the wells are filled by non-equal portions of n of eigenvalues. Then the situation is slightly more complicated. Here is the Bootstrap, this Bootstrap island. The approach is to the exact solution is much slower. You see, this is a blue region, lambda equals 6, yellow region, but then at lambda equals 11 already, it's almost perfect, at least in the picture. And it happens here, and it's just for another value of the coupling, the same picture. And it happens so here that a good approach of numerical bootstrap to the exact solution is actually on the upper bound. By the reasons I'm not sure we understood with the theorem, but somehow it's so that we see in this solvable example, we see that the lower bound is much approaching much slower with increase of cutoff. Okay, so the lesson from it is that sometimes we shouldn't just trust the inequality, but see where on the upper bound or on the lower bound the result is stabilized. Although, of course, it doesn't give you rigorous inequality in this case. Okay, so that's everything for the one matrix model. And I pass to the two matrix model. If there are no questions, of course. Yeah.
So up to now, you still have rigorous inequalities from this method, or?
Yes, and even here they're rigorous, but the lower limit, the lower value is bad here. Yes, actually at small lambda, at lambda is equals 8, for example, it's bad here, but lambda equals 11 are already quite reasonable, and still the upper limit is much closer to the exact value. So this experimenting with the sequence of cutoffs is very useful sometimes to see where it is stabilized. Okay. So if there are no more questions, I pass to the most interesting part, the two matrix model. Here, again, we use planar loop equations combined with positivity of correlation matrix of momenta, but we start from, but the set of matrix operators is more complicated. If we have two matrices A and B, indeed we have already not powers of matrices, but all possible words, all possible matrix products. A word is such a matrix product of all possible orders of two matrices with open indices so far. I mean, the two indices are open. The word has two indices. Then the moments are, of course, just traces, average traces, and large N factorization tells us that two traces factor into the average of two traces factors into averages of single traces up to 1 over n squared terms, and essentially large N already is good here because it reduces a lot the number of basic quantities with which we should work in Bootstrap approach. Only single trace quantities. Although one could imagine the generalization of this to finite n of the method. Then we write word identities, which are loop equations, like the one which we had for one matrix model. Namely, we simply put derivative under the trace before the word, and this derivative acts both on the word, on this word, and on the potential as well. And of course, it's zero if we have zero at infinity, the distribution having zero eigenvalues, for example, at infinity for A and B. And as M, we take A or B, and we make a list of all possible equations, inserting this dd mu to every word. Then it gives something like that schematically. So once you differentiate here the potential, the word is multiplied by the derivative of the potential. So this gives you a finite collection of sum of words if you have polynomial potential of given order, for example. And on the right, you differentiate the word itself, and it splits into two traces. As you know, of course, DDM hits only the corresponding matrix which you choose here, A or B. And then you have all possible splittings, the sum of the splittings. These are our loop equations, which we'll use. For numerics, we'll, of course, cut off the size of our words by the cutoff lambda. So each word contains only lambda letters, but the moments will go up to 2 lambda, as you'll see. Of course, with this cutoff, it happens that we have at each lambda, at increasing lambda, we have many more words than many more, actually not words, but moments than equations for them. They grow sort of simultaneously, but the number of equations is more and more behind of the number of conditions, of the equations. And here we should introduce some more, find some more conditions, and we choose to use the positivity of the correlation matrix, let's demonstrate it on a particular model, which is the main object of our study. It's an interesting model, sort of Young-Mills-like model, because we have commutator square here and quartic potentials for each of the matrices. So we'll essentially compute this integral in the large N limit. For the loop equation, we introduce all possible moments up to the cutoff. The cutoff is the overall number of A and B matrices in the corresponding moment. So we introduce a vector of such moments up to certain length lambda, cutoff lambda. And then suppose we have L such operators. And then we construct actually L such words. I'm sorry. I mean, here we have words, and up to a given length, we have L such words. Now we construct the same operator. We weight all these words with coefficients alpha I, sum up to all of them, and then the quadratic form is positive defined by definition. So O is here simply the sum of all these words up to given length with arbitrary coefficients alpha. So this already is not, there is no Hamburger problem for this kind of solved Hamburger problem for this kind of object, and we simply have to rely on the good luck for this bootstrap scheme. Now we can formulate the following optimization problem for the bootstrap. It reduces to the following problem. You have to minimize some physical quantity, namely, you can take, like we used W2, or you can use the linear combination of a few lowest moments to minimize and maximize, actually, to find the corresponding inequalities. You minimize them with respect to all your moments, W, which enter the problem, and impose also the positivity of correlation matrix, like it is constructed here. We have certain number of loop equations. This is the ith equation, which has quadratic form AI. The equations are quadratic here, as you noticed on the previous transparency. You have quadratic term, linear term. This comes from splitting of trace. This comes from potential, the action, and so we have to solve this problem. But the problem is nonlinear, and it is highly non-convex, which is always a problem for a big problem for optimization for programs. As Zechuan taught me, the existing nonlinear SDP algorithms are inefficient. He tried some, and it appears to be not very efficient. So Zechuan knows very well linear algebra, and he found the method in the literature which is called relaxation for this for the optimization problems, which we will apply here and reduce our problem to standard linear semi-definite programming problem with standard algorithms which work very well. And let me describe what it means, this relaxation. I hope here everything is clear, that our main problem now is that the loop equations are nonlinear. Okay. Now, what do we do for relaxation? Again, we minimize some physical quantity, linear combination of a few lowest moments, and instead of the standard nonlinear loop, the nonlinear loop equation, we introduce sort of linear loop equation. As you remember, AI is the quadratic form of the ith equation, but X we simply validly denote as a matrix of product Wk, Wj. If you plug it back, it will be nonlinear in Wk and Wj. But at least superficially, as a function, if we consider X as a new variable, it becomes linear. On the other hand, we have to somehow to apply this condition, and instead of applying the equality here, we write an inequality, namely, we construct the matrix where X is this matrix xkj, here is just one, and you have the column and the row, the column and the row of all our momenta, which you consider in the problem. So it's just the matrix of the size lambda plus 1, I guess, where lambda is a cutoff. So it's an extra inequality instead of this equality. And we'll see now that what it means. And of course, we also apply, as promised, the correlation, the positivity of correlation matrix. So now how to just justify this inequality? So we relax the equality into the following inequality. We contract the vector of all moments with alpha vector, arbitrary alpha vector. We construct this quantity, just multiply it, and it's easy to show that it's less or equal to the following quadratic, to this quadratic form. Or no, we impose this relation, which is equivalent to that one. If you just pick up the coefficient in front of alpha and alpha j, it will be x minus wwt, which is positive definite matrix. So if you take just the difference of x of left and right matrices and impose it, it's positive definite, which is we replace the loop equations by inequalities, and of course, hoping that when you apply Bootstrap with sufficiently large cutoff lambda, the inequality becomes closer and closer to equality. Now, this expression can be written by short. So this condition can be written in the form which is nice for SDP programs, in the form of positive definiteness of a matrix with linear dependence on our variables due to the Schur complement. There is a deforming property of the Schur complement that if you take the matrix consisting of 4 submatrices like Z, X, Y, T, and Y, and Z is positive definite, then if this matrix is positive definite, then the Schur complement, which is expressed like through these entries in this form, so is positive definite. That's why here we took Z equal to 1 in our case. Y, T, and Y are simply vectors of our moments, W and WT, and we get this relation, which we get essentially this relation out of here. But it's nice to rewrite it in terms of in the same form as the correlation matrix, positivity of correlation matrix. We simply have 2 similar conditions. Of course, you might ask why it should work at all, because we lose some information taking instead of equality and inequality, but somehow we know that, and we hope that at infinite lambda, this becomes again an equality, the equality, just the standard loop equations, and the loss of information also can be compensated by much larger lambda, which we can use in this problem because we have this standard SDP solvers and much greater efficiency of these solvers. And indeed, we proved it in some examples that essentially we don't lose much of information by importing it, and even acquire some accuracy, additional accuracy in calculations. And let's apply it to matrix model. There are no more questions here. I will demonstrate it in a concrete example for this matrix model. Namely, let's take the case of cutoff equals 4. We have 14 loop equations in this case on 20 moments. I don't use here average sign because it's clear that each trace is averaged here. And in addition, we have this X, which was a matrix on the previous transparency, Xij. But here we have only one variable, X, which appears to be equal, at least for this T2 symmetric states. X is expressed through this nonlinear term, like trace A square square, or trace A square, trace B square, etc. It's the same X for symmetric phase, and it enters only in the left-hand side of the equation. So only 3 equations contain this nonlinear term at this low cutoff. The rest are linear. The rest in the moments. Oh, sorry. Okay, then this is concerned with equations. They're all linear now, and the relaxation means here very simple thing. You take, instead of X equal trace A square square, you take just X greater or equal, so it's trace X A square square, and you rewrite it through relaxation matrix. The simple example of this Schur complement rewriting that this matrix is more than 0, which is obvious, of course. And you add this condition to those equations. Then you have to also, you can express these 21 variables through 7 basic variables, lowest moments, 7 lowest moments. So you use all the information from these loop equations and you plug all this into the relaxation matrix. And what is the relaxation matrix? You construct it from all words, and actually you have various sectors in this relaxation. You have various sectors for the words, even words, then only even powers of DNA enter odd, and even odd, respectively. And you have the symmetry in the problem. Then for symmetric states, the correlation matrix factorizes into 3 such blocks: even, odd, and even odd. Here I wrote the relaxation matrix. For example, the simplest, the smallest block is even odd. It is, of course, should be positive definite separately from other blocks, and you impose on other blocks, the 2 blocks the same. And then you do numerics, which even at lambda equals 4 gets sort of 1.5 orders of precision here. The inequality, or maybe 2 orders, you can view it as 2 orders of precision. That's very generic point in couplings, G and H equals 1. But it needed only 1/10 of the second on the laptop to solve it. So this is a warm-up, but my time is almost over. I have.
Sorry, you still have. Sorry, what happens a larger cutoff? Are you going to show us, because this is still quite a bit of error?
Yes, of course I will. But do you give me like 10 minutes?
Yeah. Go ahead. No
Okay,
rush.
thank you. So now I show the results for at least for Z2 symmetric solution. You have three Z2 symmetries like A to B or A2 minus A, B2 minus B. And here is the result of computation. The island around around this supposedly exact solution, which diminishes with lambda. And at lambda equals 10 or 11, you see this cross, which already is indistinguishable from the islands are indistinguishable from the cross. So it works quite well. And this is the most precise calculation in our bootstrap approach. Lambda was equal to 11. The length of operators 22. And we have 6 digits of precision for the moments trace A square. Yeah, I forgot to say that this is the axis of trace A4. This is trace A square. We have islands corresponding to the values. Each point is corresponds to certain values of these 2 moments. So you have 6-digit precision more or less for all of them. And again, these are exact equalities, unlike the Monte Carlo, which never gives you exact equalities, only with certain error bars, which probability distribution. Here are some data for the input to SDP-A solver. I never used this solver, only Mathematica, but Zechuan, who uses it, says that there are 2 kinds of solvers, A and B, and this one appears the most performant. You see 95 variables, namely moments. Sizes of correlation matrix are given here. And it needed really, as far as I remember, 3-4 days. But 6 digits are difficult to achieve on Monte Carlo. So I think maybe we've done it better, at least with the single laptop, than Monte Carlo will do. We'll see. Okay, then just I show you also a phase diagram for this matrix model, namely this gray. So this is a phase. This is a phase diagram in terms of this is a phase diagram in terms of couplings H and G, and it shows the gray area, which is shown here, where the solution is large N solution is strictly excluded. There are no solutions in this area, but in the white area there could be solutions. Or with our already we have this line with a good precision, and it can move only up right, like to the northeast. Yes, if we increase the, here we have lambda equals 8, but if we increase lambda, it can only grow this forbidden area. But we already think that it's a very good, this line is a very good precision, because we have 2 points like green for G equals 0 and red for H equals 0. These are both solvable cases of this matrix model. Either you drop for H equals 0, you drop commutator squared, and there are 2 decoupled matrix models, 1 matrix models. Or if you put G to 0, the potentials are Gaussian. It's again a solvable model, which we once solved in our paper with Nekrasov and Kostov, also Hoppe. So you see that our line passes almost exactly through these points, and with this precision, I think this line is very precise. The blue area corresponds to the limit when H bar goes to infinity for the classical minimum of the matrix theory itself, matrix model itself, but it's very imprecise then. I mean, it's very far from this line. Okay, now, okay, there are here, there are some results where we show how the inequality grows with cutoff for example, for trace A square as a function of H, here for trace A square average for the function as a function of G, we see that the more negative it is, the more we have instabilities. And somehow it happens that the lower limit gives much better approximation. You see little by little with this decrease of lambda, these lines approach the lower limit. Same here, but okay, I will not comment it too much. Maybe, okay. Then we can check how it works for solvable cases, namely when we drop this term or we drop these non-Gaussian terms. Here is the result for H equals 0, so two decoupled one matrix models. The method, and you understand, we still have words constructed from A and B, so somehow the method doesn't see immediately the factorization to matrix models. There are more complicated averages computed. But still, we reproduce perfectly the results for one matrix model here, and using the relaxation, it works at least as good as for one matrix model itself, which is very encouraging. For this is for G more than 0, and then this is for G less than 0, also for negative G's. Of course, up to the critical point where it's less and less precise, the calculation. It's less and less stable. Okay, and then for G equals 0, similar pictures. Again, you see that the lower limit, at least for negative H and G, the lower limit gives better, gives very good precision. It stabilizes around the exact solution which we know in these examples. And now, the most interesting probably case, the solutions with broken Z2 square symmetry. Namely, you have trace A and trace B non-zero, like in one matrix model. I showed what it means. You have unequal numbers of eigenvalues of A or of B in various wells of the potential. And for that, we flip this, as in the one matrix model, we flip the signs of quadratic terms, like we have double well potentials for both matrices. And now we analyze first H equals 0 case, the exactly solvable case, which is two decoupled one matrix models. And this is trace A square versus trace A moment, which is non-zero now. And then we the exact line is here. Little by little, for lambda equals 6, we don't have very good approximation. There are points of numerics here by red, but the upper limit is quite good. And then for lambda equals 9, it's already much better, but still the upper limit is much better approximation to the exact solution than the lower limit. Okay, and then finally, maybe the most non-trivial case, the solution with broken Z2 symmetries for generic point. This was the point H equals 0, which is solvable, but here finally we have Bootstrap for sort of generic values of parameters, but we know that these parameters correspond to symmetry broken phase already. And this is the computation, the best computation is at lambda equals 8. And we sort of looking at these graphs, we know that the exact value should be close to our upper limit, because the problems are very similar. So we simply relax the condition that H equals equal to 0. So, and from going from smaller lambda to bigger lambda, we see that the solution is stabilized on the upper on the upper bound here. And we can read off the values from the upper bound and hope that they're quite precise. I think, but these values, I guess after we published the paper, these values were lost, but because the laptop of Zhechuan was stolen in his office with all this numerical data. So I cannot give numbers here. Okay, and then finally, the last transparency before the conclusion, it's comparison to Monte Carlo. And the results of Monte Carlo are reported to Rogav Govind Ya, probably the PhD student of postdoc, I'm not sure, in perimeter, which will be published soon. He simply has done the Monte Carlo with the same model and with our parameters, which was very helpful in comparison. And he kindly agreed that he show these results before he publishes it. So Monte Carlo procedure, he found the density, say in the symmetric phase for G and H equal 1, unbroken phase. He took the matrix integral at n equals 300, quite large, but finite. In our Bootstrap, it's by definition infinite. And this is how the density of eigenvalues looks like. It's quite narrow if you look at the numbers here. This is the relaxation process of Monte Carlo in some, I think in terms of minutes, I think it's a few hours, which he needed to get 3 digits of precision for these two momenta. To compare with our case, which I showed before, this kind of islands of decreasing size, this is our best result, 6 digits. It took a couple of days, of course. If we used smaller cutoffs than lambda equals 11, I guess we used here, then to get 3-digit precision, we needed only, I mean, for Monte Carlo, it's a couple of hours, a few hours, as you see here, a few hours on a single laptop. For us, it's like 10 seconds for Bootstrap method. So we see already that Bootstrap can have, in certain circumstances, can have much better performance than the Monte Carlo. And here is the broken phase results, again for n equals 300. Actually, here is the relaxation for 2 different moments. But somehow in this experiment, he chose the middle point where the symmetry is not broken. It's in broken phase, but it's a continuum of solutions along this line. And he chose this point. But quite a couple of days ago, he sent his data already for this completely broken. Sorry, this is trace A simply, not trace A squared. This is trace A squared. He sent his data, which are quite good. We have like 3 digits precision for this point, and for us, for the Bootstrap, it was quite a lengthy calculation, but we restored the whole line of solutions in our calculation. So it's only 1 point. Of course, we can put more and more points here, but it will take also time. Okay, this is the comparison, and I finish with, if there are no questions here, I finish with conclusions and prospects. So I hope I convinced you that matrix Bootstrap is an interesting alternative to Monte Carlo for the computation of various functional integrals, and especially efficient it is at large n, for large n problems. It gives exact inequalities on physical quantities. The method inherits some ideas of you guys of the conformal matrix Bootstrap, which is at the heart of your Simon's collaboration, but it's a new direction aiming at sort of different kind of physical problems, and that's why I found it's sort of an interesting direction to work on. To overcome the non-convexity of nonlinear loop equations, we proposed to use the relaxation procedure. This is our conceptual contribution. And unlike the master field method of the later work of Demela-Koch et al., the relaxed bootstrap method has a few advantages: exactness of bounds at a given cutoff, absence of convexity for the relaxation approach, and simple and physically very, very transparent algorithms as well, because their approach is, the equations are quite nonlinear. It's sort of a sophisticated variational method, I would say. But combining two approaches would be very promising, in my opinion. And of course, the number one problem to solve is the lattice Young-Mills theory via mechanical loop equations at various dimensions at large n. In this respect, the pioneering paper of Anderson and Kruchensky was very important, but the results so far are not very convincing, and we need to improve the tools to improve the results.
Sorry, can you apply your methods there? Could your methods be useful for this?
Absolutely, we are pretty sure, because actually the bootstrap matrix bootstrap was sort of read off by Henry Lin from the, I think, from the paper of Kruchensky and Anderson, the same kind of equations. In 2 dimensions, it works very well, but for 3 and 4 dimensions, it is not yet very convincing, but at least it's an alternative. And we didn't see alternatives in solution of Young-Mills theory for many, many years already. Okay, and but we need, of course, some new ideas to inject some additional information about, say, higher moments in loop equations, and to reduce the size of correlation matrix. There are various directions to work in, and I hope this method will be really a good alternative to Monte Carlo. Thank you very much. Yes.
Thank you very much. I have a few questions, but let's wait for others to ask questions first. So one question I have is that you are focused on this calculation of these moments, but sometimes some of the most useful physical observables are not necessarily moments. For example, expectation values of macroscopic loops. Those are the kind of things that you could compare, for example, in the old days of low-dimensional string theory, compare them with Liouville. And is there any idea of how to incorporate these kind of observables?
Say, in 2-matrix model, we have just moments, but long loops also, long loops would, the analog of long loops would be just long words, yes?
Yes.
Take trace A to some power times trace B to some power, big power, for example, it will be sort of a loop, but they are not closed, of course, but in Young-Mills, in mechanical equations, you just should list all the loops up to a given order. But of course, you don't have access then to very big loop. Maybe that's your question.
That's my question, yes. So for example, when people were, I think you included, were comparing the results of the double scale matrix models with Liouville, some of the most direct things you could compare were these microscopic loops operators in terms of Liouville boundary states and things like that. But that would be a different limit, right? In which are
that's a different limit. We start from small loops, but there are ways to interpolate, to extrapolate. Sorry.
Yeah, but my question whether there could be a different limit that you take that directly access this kind of different observables.
No, but you just don't have for those such loops. You should take all loops in this approach. You should close the loop equations as much as you want, as you can. Sorry, but if you just pick up big loop, in Monte Carlo, it's a good problem, but not for the Bootstrap. You really solve loop equations.
I don't think there could be some modification where you're, because from the worship viewpoint, this is like putting a boundary, right?
Yes.
So couldn't there be some sort of modification where you look at some sort of boundary loop equations or something? I don't really know what I'm saying, but
I think this is this is very vague proposal because okay, you pick up a couple of big loops. What do you do with them? But you can maybe reach some information about them by using, for example, this master field approach, which Anderson Krulchensky, which actually Demelo Koch
and a related question here, you are working for fixed value of the Toff coupling, but could you imagine somehow taking the double scaling limit and working directly in the double scaling limit?
You speak about the, say, two matrix model, like you tune to the critical point and work in the double scaling limit.
It's just a vague suggestion. I don't know, but
yeah, because no, I think it's a good question, but the method is completely orthogonal to this kind of large loops. Because
no, never mind large loops. Even for never mind large loops. Like if you could somehow directly access the double scaling limit.
If you know the double scale potential, like in one matrix model, you can immediately start from double scaling limit, as you know. But if you start with say our two matrix model, which is not analytically solvable, you can try to reach this point, of course, by tuning the potential better and better to the critical point and work around it. I'm sure it is a very unstable point, as we saw already in solvable cases. So it will be not a single calculation, but in principle, why not?
I mean, the more general question is, so what kind of physics can we do with these interesting matrix models? And some of the physics that I know of is in this double scaling, but maybe there is some other interesting physics that you can do with this.
Yeah. With this. For example, because I work so much on various matrix and multi-matrix problems, I have my favorite problems which I wanted to solve but never solved. For example, if you start putting the matter fields on your graphs, they usually, like for Ising model, they are described by various spins. And the directions of spins correspond to the matrices, to the type of matrix. Then, for example, you can consider the model where the Feynman graphs interpolate between completely random and completely regular graphs like fishnet. If you put spins on these graphs, you can interpolate between the physics of gravitational physics with matter fields and the one without fluctuating matrix, which is modeled by graphs, by Feynman graphs. So, for example, this kind of models. No, I'm sure there are many models of this kind. And the most interesting, of course, is Yang-Mills itself, because in Yiguchi-Hawaii reduction, the four-dimensional model is just the model of four matrices. Yes. So the Yiguchi-Hawaii formulation of Yang-Mills is just a multi-matrix model in large N. So probably there are many more applications, but it doesn't come to my mind immediately.
And final question.
Another
There have been a
application,
few papers. There are a few papers. I
sorry,
think
another
you
application.
cited it.
Sorry, Leonardo.
No, go ahead.
Of
Sorry.
course, I should mention this matrix theory of superstrings, like IKKT model, the FSL model. People already have been trying to apply Bootstrap. There are late works where people try to apply to these models Bootstrap. So here is an application which you might like.
And there was in the different set of papers they were doing, they were bootstrapping matrix quantum mechanics, right? I think you cited some of them. Do you think that similar methods could work there, or?
Of course, of course. For example, the problem which I would like to solve and I never solved is to apply, say, to solve the black hole, to them this the Platonic black hole in terms of matrix model, you know, quantum mechanics with vortices, which models the vortices and the worldsheets, etc. But if you introduce interesting quantities, which, for example, which can be formulated in terms of matrix integrals, which can measure subtle quantities like maybe Hawking radiation, you will not solve for these quantities, and probably the Bootstrap approach can do something. So
Thank you. Any further questions? Okay. Sorry, you wanted to finish. You wanted to say something. You started to say something.
No, this was the end of the phrase. That,
okay.
The application.
Thank you very much, Volodya. Thanks, everybody. And thank you.
Thank you very much. Thank you.
Thank you very much for a nice talk. Thanks.
Thanks a lot.